Hello, welcome again. Today we are going to discuss a very important component of IB diploma syllabus, that is point of inflection, which is spelled as XION or ECTION. So point of inflection is something that is part of SL and HL, both it is section 5.8. So before we start with point of inflection, I would like you all to recall few important concepts like what is an increasing function, what is a decreasing function, what is the stationary point, sorry, local maximum, local minimum, and also what is concavity, concave up and concave down. So let's get started. So let's explore all these things with the help of this curve. Let's say fx is a function, y is equal to fx. Now, if you see in this, this is obviously a quartic function in which we see function comes down when value of x increases, value of y decrease at certain point, then it increases till this point, then it decreases again, then it increases till infinity. Now, if you closely look at, let's label it as A, B, C, D, E. If you closely look at this part, A, B, from A to B, what happens when the value of x increases, the value of y will decrease. So as a result, what happens? When we draw a tangent here, the gradient of tangent will be negative. So this part of curve from A to B, please remember B is not included. From A to B, this part is called a decreasing function. Since the gradient is negative, so at all points in a decreasing part of a function, or if it is a strictly decreasing function, and then at every point in this function, f prime, that is the derivative, first derivative will be negative or less than 0. Now, let's move on from B to C. If you look at from part B to part C, as x increases, we see y is also increasing. As a result, the gradient will be positive. So this part of the curve we can say is an increasing function where gradient is always positive. Moving further, if you look at this part from C to D, now what happens from C to D? Similar to A to B, C to D also is your decreasing function where the gradient will be negative. And moving further from D to E, when x increases, y will also increase. So gradient is positive, hence this is increasing part of the function. Now, if you see, there are a few important points here, point B, point C and point D. Now, when you draw a tangent to these points, what happens? Tangent is always parallel to x-axis, or we call it a horizontal tangent. A horizontal tangent means the gradient, that is dy by dx, or tangent of x, which is tangent of 0, will be 0. Also, if we see, your graph is turning at these points from decreasing part to increasing, then increasing to decreasing, then again decreasing to increasing. So these points are also popularly known as turning points. Also, if we see, dy by dx at these points is 0, and dy by dx means the differentiation means change. So there is no change, so these points are stationary points. So another popular name for these turning points or these vertices is stationary points or turning points. So this was a decreasing, increasing function and turning point. Moving further, concavity. So there are two types of popular functions. One is concave up and concave down. So concave up we can consider as, if you put your hands upward, so the function that is formed is called concave up function, or a concave up function is a function that resembles an upward facing bowl or a cup. For example, this is your bowl, soup bowl or noodle bowl. So if we take a curve which resembles this, so this sort of function which looks moving up, these functions are called increasing functions. Now what happens in increasing function? From this top point coming down till this vertex and further going up, at each point when you draw a tangent, that the gradient of tangent, it may be positive, may be negative, but the value of the gradient will keep increasing when x increases. So the gradient will increase as x increases. As a result, when the gradient is positive, change in the gradient, that is the second derivative, this will be uh, positive because it is an increasing function, I mean the increasing gradient, so its second derivative will be positive. Similarly, if we look at concave down functions are when you put your hands down like this and it resembles a downward facing ball or a cup, something like this. So if we generate a function, this is how it will look. So let's move this ball. So this sort of functions are called concave down functions. In a concave down function, if you move from left to right, then what happens when you draw a tangent? Gradient of tangent will keep decreasing. When it keeps decreasing, then what happens? Its gradient, that is gradient of gradient, means the second derivative will be negative for concave down functions, right? Moving further. Let's go back to the same curve that we used before. So let's label it as A, B, C, and D. Now, in this function, if you look at this part of the function, which is highlighted in blue, this is obviously a concave down part of this function. And if you look at this function from A to this blue line, this is a concave up function. And this red part is also concave up function. There are few points, like a point is here, a point is here. So these are very special points. Now what happens at these points, if you look at this point and that point, so there are lots of things happening at this function. Some of those are concavity of graph changes at these points. So your graph is concave down, concave up till this point, then it changes to concave down till this point, then it moves further up to concave up. So concavity of graph changes. If it is concave up, it becomes concave down. If it is concave down, then it becomes concave up. Also, the change at these points is either highest or lowest. This we will discuss in detail later. This is one of the tests to check point of inflection. So at this point, remember, first thing is concavity. It changes from concave up to down or down to up. Second thing is the change, that is rate of change or dy by dx is either highest or it is the lowest at these points. And these special points are called points of inflection. So second derivative is always 0 because dy by dx is either highest or lowest. So going back to the concept of maximum, minima or stationary point, when dy by dx is highest, its derivative will be 0. When it is lowest, its derivative is 0. So always remember that second derivative, that is d2y by dx squared, is always 0 at these points. And these special points are called points of inflection. Moving further. For a function y is equal to fx, a point of inflection is a point where what all happens? Number one, y is equal to fx changes its concavity. If it is concave up, it turns to concave down. If it is concave down, it changes to concave up. The second thing is the rate of change, that is dy by dx or f prime x, is either takes a maximum value or it takes a minimum value. Again, we can classify these points of inflection as a point of inflection which is stationary, and we all know that a stationary point means the first derivative is 0. So if the second derivative is 0 and the first derivative is also 0 at point of inflection, we call it a stationary point of inflection. If the second derivative is 0 but the first derivative is not 0, we call it a non-stationary point of inflection. Moving further, what is the working rule to find a point of inflection or points of inflection in a curve? So let's say y is equal to fx as a function. So first thing what we do, we find its first derivative. So find dy by dx or f prime x. Then we find the second derivative, that is d2y by dx squared. Now, the necessary condition, there are two conditions here, necessary condition and the sufficient condition. The necessary condition is second derivative of function should be 0 at the point of inflection. So, from here you put d2y by dx squared is equal to 0. And remember that this is a necessary condition. It has to happen. However, if second derivative is 0, it does not mean that the function is or the point is going to be a point of inflection. There are more tests which we will see now. Now, since the concavity changes, and we know that for concave up, what happens? Second derivative is positive. For concave down, the second derivative is negative. So, what we do is we check the sign of second derivative around the x value or values that you obtained in number 3. If you see there is a sign change, means it is a point of inflection. If sign does not change, it is not a point of inflection. If the sign of dy by dx, d2y by dx squared changes around x values obtained in part 3, this will be the point of inflection or points of inflection. Moving further, let's explore this more with the help of this example. Consider a function 3x4 minus 16x cubed plus 24x squared minus 9. Find and classify all points of inflection. When it says classify, means we need to classify whether it is a stationary point of inflection or a non-stationary point of inflection. So let's start. This is your function fx. So first step is differentiate this. So your f prime x will be 12x cubed minus 48x squared plus 48x. Second step is you differentiate this again. So second derivative is 36x squared minus 96x plus 48 and equate it to 0, because the necessary condition for a point of inflection is its second derivative should be 0. So when second derivative you equate to 0, you get this equation. When you solve this equation, you get two values of x. X is equal to 2 or x is equal to 2 by 3. Now, at these 2 points, you may or may not have a point of inflection. So how do we check? Check the value of the second derivative around these 2 points. When I say around, check at 2, it will be 0 obviously, and little less than 2. When I say less than 2, don't go up to 0, 1 or negative 1. As close as you can, maybe 1.99. On the right side, maybe 2.01, etc. You can do it with the help of a calculator, and if you use TI Inspire, it's so easy. In TI Inspire, first to define your function, check the value at 2, it is 0. At 1.99 means on the left hand side it's negative, on the right hand side it's positive. So the concavity of the function changes at x is equal to 2. Similarly, when you find at 2 upon 3, it's 0. 2 upon 3 is 0.66. So when you check on the left hand side, I have taken 0.65. It is positive. On the right hand side, it's negative. So again, concavity changes at both these functions. So both these are points of inflection, x coordinates of points of inflection, remember. Now we have to check the classification, whether it is a stationary point of inflection or a non-stationary point of inflection. So how do we do this? Put x is equal to 2 in the first derivative. So when you put it in first derivative, it is 0. So this will be a stationary point of inflection. And when you put in x is equal to 2 upon 3, the value is approximately 14.2, which is not 0. So it is a non-stationary point of inflection. So when you put x is equal to 2 in the main equation of the function, you get the y coordinate, which is 7. And same when you put x is equal to 2 upon 3, y is negative 2.48. In the exam, when they ask you to find point of intersection, you need to find x and y coordinate both. Finding x value is not enough. So these are 2 points of inflections. Now, we can find or check whether it is a point of inflection or not with another method using the first derivative. How do we do that? Let's take the same example. Sorry. This is a function, find and classify all points of inflection. So we start in same fashion. We find the first derivative, then we find second derivative and put second derivative equal to 0. Now, if you remember, we discussed that point of inflection is the point where the change is either highest or lowest. So when we are talking about change, so the sign of first derivative will remain same on both sides of this point. So now what we do at these 2 points, second derivative is 0. So we check the sign of first derivative around these 2 points. So again, I have used TI Inspired CX calculator. I define the first derivative as function hx, h2 is 0. And at 1.99 it's positive, at 2.01 it's positive. At x is equal to 2 upon 3, first derivative is this, and on the left hand side and right hand side it is positive. So it confirms that x is equal to 2 and at x is equal to 2 upon 3, we will get point of inflection. Now h2 is 0 and h2 upon 3 is not 0, so we can conclude that at x is equal to 2, you will get a stationary point of inflection, and at x is equal to 2 upon 3, you will get a non-stationary point of inflection. And of course, you need to find x and y both. So it's 2, 7 and 2/3, negative 2.48. So this is how you can find point of inflection and find its nature, or you can classify it. Point of inflection is widely used in so many areas. Like if you see in economics, in business growth, or inflection point can mark a significant change in a company's growth rate. So the highest growth or the lowest growth we can find in epidemiology. We can model a pandemic spread using it. In physics, when you have velocity versus time graph, then we can see when the acceleration is highest or the lowest, because acceleration means the second derivative. When you have displacement, then velocity, then acceleration. So when the when the acceleration is highest, velocity is highest or lowest, we can use point of inflection. So that's all in point of inflection. And if you found this video useful, consider subscribing it, and soon you will see many more videos, short videos of such nature. And any comment, feel free to write at jalajmaths@gmail.com. Stay safe, stay blessed, take good care. Bye-bye.